Okay, welcome back, everyone. Our next speaker is going to be Linbo Wang, who is an assistant professor, at the University of Toronto. He did his PhD with Thomas Richardson, and then at University of Washington, and then moved to a postdoc at Harvard School of Public Health in causal inference, and then joined the University of Toronto a few years ago. And he's going to be talking about the promises of parallel outcomes. So, do you want to share your screen, Linbo?
Okay, thank you, Rob, for the introduction. I think I'm kind of outlier here. I'm not going to talk about anything about randomized trials, but I will only try to use observational data to make causal inference. So this is based on joint work with my former PhD student Injo and my colleague Dehan. So I'm going to trying to estimate the effect of exposure X on outcome Y. For example, people in Alzheimer's disease may be interested in estimating, say, a biomarker level, such as tau protein on some cognitive functioning. So usually in practice, how we measure this outcome Y cognitive functioning is through a sequence of cognitive tests. So this is a questionnaire that you have different components which is supposed to test the functions in different parts of your brain. So you get a score for each of these tests, and usually what people use in practice as an outcome is the sum of scores across these different parts of the test. But we're faced with the classical problem of unmeasured confounding here. In particular, there's a major unmeasured confounder that is underlying disease progress. Right? Obviously, this disease progression will affect this biomarker level, such as tau protein, and this is exactly why these things are called biomarkers. And on the other hand, we know that the disease progression will also worsen your cognitive functioning. So this is unmeasured confounding. So there are different ways to deal with unmeasured confounding. The gold standard is to have a randomized controlled experiment. So it's true that, but we know that we cannot randomize the disease progression here. So this is not an option. So another assumption that people often make is that we have measured all the confounders. So it's true that we can measure this AD progression through pathology, but we cannot do pathology when people are still alive. And so instead, what I'm trying to introduce in this talk is a new framework for making causal inference to deal with unmeasured confounding by leveraging this information in these multiple outcomes we have. Right here in this test, we not only have an overall score, but we have these subscores from different parts of the test. I'm trying to use this information contained in these multiple parts of the test to help us mitigate bias due to unmeasured confounding. And so here's the setup. So I'm going to be interested in estimating the effect of one treatment on on multiple outcomes, Y1 to Y3 here, for example, that are affected by the same treatment and unmeasured confounded U. Okay, of course, if U is unmeasured, then we know how to identify this mean potential outcome at least. We can do this through this G formula. But the problem here is we don't observe this this confounded U. So a key assumption in our framework, this is what we call the parallel outcome assumption, is that we're going to assume that these multiple outcomes are conditionally independent given the exposure and the outcome and the unmeasured confounded yield. So on the graph, this means that we have removed the arrows among these multiple outcomes. So these are multiple outcomes cannot influence each other directly. So in the Alzheimer's disease example, this will mean that we will need to select a few subscores and conditioning on the underlying disease progression and this biomarker level. These multiple outcomes will need to be condition independent, so they cannot directly affect each other. Another example where this kind of setup may arise is in genetics in gene expression analysis, where people are often worried about the unmeasured confounder, which is a batch effect. You may be interested in the effect of one particular exposure on multiple gene expressions simultaneously, but they may be all be subject to batch effects. So what people have been doing in genetics is they have been assuming these linear models relating the exposures with gene expressions, and this is called surrogate variable analysis. And one common assumption they've made is that the error epsilons, the noise here are independent, or the covariance of this epsilon are diagonal. And this assumption that people often made in practice actually implies our parallel outcome assumption that conditional X and U, these multiple outcomes are condition independent. So here's a nutshell of the main results under this framework. We show that under this parallel outcome assumption, as long as you have at least 3 parallel outcomes, then the causal effects will become non-parametrically identifiable. And if you are willing to make more parametric assumptions, such as linear structure equation models, then the number of outcomes you will need for identification is reduced from 3 to 2. So in other words, you can replace one of the parallel outcomes with the parametric assumptions. So before I go any further, I would like to contrast this framework to some existing frameworks for dealing with unmeasured confounding. The most popular framework nowadays may be the instrumental variable methods that requires you to find the instrumental variable that's exogenous to this causal problem we're interested in. So another framework that's recently become very popular is so-called negative controls. So you need to find a set of negative control exposure and a negative control outcome so that will satisfy certain identification assumptions so that you can estimate effect of X on Y. So what's common to these approaches is you need to collect some additional information that is exogenous to this causal system you are interested in. But in comparison, this parallel outcome framework doesn't require you to collect additional data beyond the multiple outcomes that is often already exist in your data set. And I also want to contrast this framework with the multi-cause causal inference framework, look very similar on the surface. So in this multi-cause causal inference, people look at the effect of multiple exposures on one outcomes. So this seems to be symmetric to our system, but I will show you that they are fundamentally different. They are going to make, the key assumption there is also very similar to the assumption we make. They assume that this conditional independence among the exposures conditional unmeasured confounded yield. And on top of that, they're going to assume a linear structure equation model for the treatments. So a vector model relating the multiple treatments. But unfortunately, it has been pointed out that even under this additional linear model on the treatments, it's not possible to have non-parametric identification under this multi-cause causal inference framework. Previously, we have shown that if you are willing to make some additional parametric outcome model assumption, then yes, indeed, you can identify the causal effects. But we know that it's often quite dangerous to place all your bets on these parametric assumptions, especially if you are using them for identification. So as Carsten Dinelli puts it, if an issue can be addressed non-parametrically, then it will often be better to tackle this parametrically. However, if it cannot be resolved non-parametrically, then it's usually dangerous to resolve this parametrically. So, so this is indeed the main advantage of our system, of our framework compared to this multi-cause causal inference. Right? What we'll show is that as long as you have 3 multiple outcomes, then you will indeed be able to identify the causal effects non-parametrically without any additional parametric assumptions. So now, please let me go into a little bit details of trying to explain the intuition behind our identification results. So I'm going to illustrate this idea under a simple binary model where I'm going to assume that everything on this graph, U, X, Y1, Y2, Y3 are all binary, just to give you the main idea here. And I'm going to use my favorite technique in causal inference, which is counting the number of equations and the number of parameters. And so here on the left, I have my observed data distribution, which is Y1, Y2, Y3, conditional on a particular value of X. And on the right, because of the conditional independence assumption I have, I can write this as a summation over some products of unknown parameters. So what's right on the right-hand side, these blue terms, these are unknown parameters that I try to identify. And these parameters are known because they involve unmeasured confounders U here. Okay, so now we can count how many equations we have and how many parameters we have. On the left-hand side, we're looking at a joint distribution of 3 binary outcomes. So this will give us 7 independent equations. On the right-hand side, for each x, because y is binary, so we get 2 parameters here, one for u equals 1 and one for u equals 2. Similarly, 2 parameters here, 2 parameters here, and lastly, 1 parameter here for fixed x. So in total, we have 7 equations on the left and 7 equations on the right. So this problem looks promising. We have the same number of equations and the same number of unknown parameters. But we're not there yet because these are nonlinear equations, right? So we cannot directly solve these nonlinear equations. So here I'm going to talk about explain the details of how I solve these nonlinear equations involving products of parameters. So my first step is to is to take the summation over y1 on both sides of the equation. So the idea here is that by taking the summation over y1, this term involving y1 disappears on both sides of the equation. So the idea here is if we can somehow ignore the summation over u, then we can just take the ratio of these two equations and identify this red term over here, which is the probability of y1 given u and x. If we can do this, then we can use the same logic, identify probability of y2 given u and x, or probability of y3 given u and x, and then lastly, probability of u and x, u given x. But of course, we know that we cannot do this. Like we cannot just ignore the summation and take a ratio here. But instead, I'm going to use a technique called the matrix adjustment method. So the idea here is to write the summations here in terms of matrix multiplication. So here, every term here will be a matrix, and this PD here means this is a diagonal matrix. So this is not the same, exactly the same as what's showing what I showed above, except that I just write this multiplication in terms of matrix multiplication. You can see that I can try to apply a similar idea as before. If I can somehow divide the first line by the second line, then I can still identify this matrix here, which will correspond exactly to the probability of y1 given you the x above. And in fact, we may be able to do this for matrices. And the way we do this is to multiply the first term by the inverse of the second term. So indeed, a lot of terms here cancels out. So what we are left with is not exactly what we want. Is besides the red matrix that we try to identify, we still have 2 other matrices lingering around here. But if you take a closer look, you will see that this is okay because this is nothing but the form of an eigenvalue decomposition, right? This first matrix here is a square matrix multiplied by a diagonal matrix multiplied by the same square matrix inverse, right? So this is exactly the form of eigenvalue decomposition. So we can just apply eigenvalue decomposition to the left-hand side and identify these eigenvalues as the diagonal elements of this matrix. And this is the key idea behind our identification. So this reasoning can be generalized to a general model where we not necessarily have a binary outcome, binary treatment. It can be generalized to any categorical, to any outcomes with categorical levels. And in fact, if you apply some other techniques, it can be generalized to continuous outcome as well. But I'm just showing you some additional conditions here. So the first condition requires that there is no qualitative U-X interaction, meaning that the confounding effect of U on Y will have the same direction across all the treatment levels. So what that means in this Alzheimer's disease problem is that we're assuming that as the AD progresses, then each of these outcomes, it doesn't matter if the calculation or orientation or recall, all of these cognitive ability become worse over time, regardless of the biomarker level. And this seems to be a plausible assumption in this context. The second condition we're going to assume is a particular full rank assumption that only involves the observed data. So this assumption can actually be tested, at least in principle, from observed data. And our result says that under these 2 additional assumptions, not only the mean potential outcome, the potential outcome distributions are actually identifiable if you have at least 3 outcomes. Okay, so now that we have these non-parametric results, we can try to make our life a little bit easier by making some additional parametric assumptions. And in particular, I'm going to assume a sequence of linear structure equation models relating my treatments and these outcomes. And in this case, the parameters of interest here will be this beta 1 and beta 2, and in this structure equation models denoting the effect of X on Y. So we show that under some additional conditions, then we can indeed show that these causal effects will be identifiable. And I will explain the meaning of these additional conditions in the data example. In the data example, we'll be interested in, as we said, the effect of tau protein level on two outcomes. One is decline in orientation score, and one's decline in recall score. And the data we use come from the Alzheimer's Disease Neuroimaging Initiative, or ADNI. We have 925 subjects with complete measurements, and we're going to adjust for some measured coverage such as age, gender, and education. So in this context, the two conditions we make is first, we assume that the error terms here, so epsilon x, epsilon 1, and epsilon 2, they're all symmetric around their mean. And another assumption that we're going to assume is the U, which is the underlying disease progression here, is asymmetric. So the idea behind this is the disease progression will not have a symmetric distribution, right? For most healthy people, probably you have very little disease progression, and but for people who has already developed AD, then this is the tail. You will see a very long tail. Someone has progressed to mild cognitive impairment. Some people develop for AD and very serious disease. So these conditions are not testable, directly testable from the data set because it's about these error terms and these unmeasured confounders. But these conditions does have some testable implications, right? In particular, if we look at these equations here, if we regress out V from the first equation, then the residuals will be a linear combination of U and epsilon X here. So the residuals here will be asymmetric. And similarly, in the Y model, if you regress out X and V, then the residuals should also be asymmetric because it's a linear combination of an asymmetric U and a symmetric epsilon term. So we can test this in the data set we have. So the first plot here is a residual plot of the tau level here. And you can see that this plot is indeed quite skewed. And this means that for most people, the tau level is very low, but for people who has developed AD, this level can be quite skewed. And these two plots are the residual plots for the outcome. And similarly, you can see that these plots are not symmetric. So here is the estimation results from our method. So after adjusting for this unmeasured confounder U, you can see that we still the adjustment effects still have the same direction, which means that the higher tau protein level still leads to acceleration in cognitive decline in both the orientation and the recall abilities. But if you compare this adjusted estimates to the crude estimates, you can see that these effects are attenuated and this is because of the adjustment of the unmeasured confounding. Okay, so I think I have 1 minute, so I will have a quick summary of the talk. So we are trying to address the key change to causal inference from observational studies, which is unmeasured confounding. And unlike the other speakers on this session, I'm only going to use observational data and not going to use any additional randomization to help me identify this. So instead, what we try to use is to leverage the information contained in the multiple outcomes. And in particular, we assume a condition-independent structure among these multiple outcomes that we may have. And I think this is particularly promising for analyzing high-dimensional response because in practice, often we have more than 3 outcomes. We may have a high-dimensional outcome, so we have a lot of extra information, and we have seen that it's possible to use this extra information in this extra outcome to relax the condition independent assumption, so to make this framework somewhat more plausible. So our paper is on arXiv and has just been accepted by Biometrica. And the slides is also available on my website. And thank you very much for your attention.
Thanks very much, Limbo. Little virtual clap for you there. Does anyone have any questions they'd like to ask? Yeah, please go ahead.
Hi, Limbo. Yeah,
Hey,
thanks for a great talk. I guess I have two questions. One of them is this seems really related to proximal stuff, because it sort of seems like your outcomes are kind of acting like proxies for each other, and I was just wondering if you had any thoughts on the connections there. And the second question that I had is in like establishing an explicit identifiability map, like in missing, sometimes you don't need to worry about it, right? So in missing data problems, if I know that the full data distribution is identified somehow, I don't necessarily need to know what exactly the form of every identifying formula is. I can just maximize the full data likelihood. I can maximize the regular missing data likelihood, right? And then the fact that everything identified, you know, the existence of a unique maximum is taken care of for me, even if I don't know implicitly what the form of it is. And so I was just wondering if that helps you here. Like if I just maximize the likelihood for a model like this,
okay,
like
yeah.
why do I need to worry about the explicit functional so much?
Okay, great questions. Yeah. Okay, yeah, thanks. Great question. So the first question is the relation with the proximal causal inference framework, right? So if you take this Y1 as your sort of primary outcome, then Y2 and Y3 are actually satisfy the conditions for native control exposures. So you can think of this as, so the classical results, you need one native control exposure and one native control outcome. So here I'm showing you that as long as you have two native control exposures, that are conditionally independent of each other. Because the native control outcome and exposure, they don't have to be condition independent. But here I need these two native control exposures to be condition independent of each other. So as long as you have these two, then you will be able to identify the effect for your primary one. So that's the connection here.
Okay.
And the second one is, so you're suggesting just maximizing the likelihood as long as this is identified, right? So great, but the problem is that this is not yet identified. Because here, if you have this equation, turns out if you don't have these additional assumptions, then this is only locally identifiable. So I think you do this exercise to figure out what are the additional assumptions to allow you to identify this. Yes, when I do this, after I do this exercise, I figure out all these conditions, then yes, you can just apply your MLE to estimate these parameters. It's no problem. But the question is, it's not yet identified at that stage.
Okay, I understand. Thank you.